Hi, my name is Patrick Vaughn, and today I will be discussing Lab 1, which has to do with the constant velocity and Newton's second law of motion. I do this through the use of a computational and observational model. First, I will explain Newton's second law of motion. The equation for Newton's second law is force equals mass times acceleration. However, if there is no net force, there is no acceleration. If this is the case, if velocity equals 0, the object will remain at rest, and if velocity does not equal 0, the object will remain in motion at a constant velocity. At the bottom, I have the equation for velocity in meters a second, which equals change in position in meters over change in time in seconds. Here are my initial parameters for my observational model. As you can see, for my axis, the positive x direction points to the right and the positive y direction points upward, and I assume mass is constant. Here's the tracker video that I used. As you can see, I rolled a ball at what I perceive to be a constant velocity. And here's the linear graph of change in position over change in time that I got from this data. As you can see, my tracker model started at 0 seconds and 0 meters. And this data is what I use to compare to my computational model data. So here's my glow script code that I used to create my computational model. And here are my initialization conditions. I set the ball's mass equal to 0.65 kilograms, the ball's position equal to 0 meters, and the ball's velocity equal to 0.909 meters a second. I also set time equal to 0. I set delta t equal to 0.01 seconds. This is the change in time. Basically, I set this to as low as it possibly could go in order to get more data points and have a more accurate model. I set net force equal to 0 because we want this model to be running at a constant velocity. I set the ball's velocity equal to the previous velocity plus the net force over the ball's mass times the change in time. This is the implementation of Newton's second law. I also set the ball's position equal to the previous position plus the velocity times change in time. This is the velocity equation. And here's the computational model. As you can see, the position versus time graph is linear, and the velocity versus time graph is constant. Here's the comparison between the predicted and observational data. As you can see, there's a differentiation between the two data types. This is mainly due to friction and air resistance on the observational model. It is possible that this happened. This is due to friction and air resistance on the ball in the observational model. The observational model started to slow down and deviate from a constant velocity at about 0.1 seconds. This means that there was a significant amount of friction applying to the ball. If the axes were flipped in my tracker model, then I would have had to equate for that and set my computational model to a negative x direction so that they could be compared. It is impossible to say how many forces act on the observational model because the force of friction I might be able to calculate that, but I will not be able to calculate the force, all the tugs that the air does on the ball. And I won't be able to compute the exact friction in the z direction on the ball either. This concludes my presentation. Thanks for watching.